Hello everyone. After Carnot cycle, our next topic of discussion in the lecture number 22 is refrigeration. Refrigeration is following the same type of cycle, the Carnot type of cycle, but its sequence of operation is something different from that of Carnot cycle. Here we start our journey from the same reversible isothermal expansion of an ideal gas, but the next step, instead of expansion, it would undergo compression. That means it would be adiabatic reversible compression, so B to C. And then C to D is isothermal reversible compression, and then finally come back to the initial state A by means of adiabatic reversible expansion. Okay, so here initially the temperature, pressure and volume were P1, V1 and T1, and here the temperature remains unchanged to T1, but the pressure has decreased to P2 and volume has increased to V2. Then after compression, the pressure has increased to P3 and the volume has decreased to V3, and simultaneously the temperature also increased to T2. Then C to D, here the pressure has further increased to P4 and the volume further decreased to V4, but the temperature remains the same, T2. Okay, and finally coming back to state A from D to A by adiabatic reversible expansion to P1, V1 and T1. And from A to B, the machine is taking up Q prime of amount of heat from the surrounding. Okay, so the second law says that it is impossible for a self-acting machine to take up heat from a body and releasing to another body which is at higher temperature. But here we are making it possible, but we have to provide some work, and that work is W amount of work. That work combines with this Q prime amount, and then its summation Q prime plus W, this amount is actually Q, is being deposited to the system. So by this technique, refrigeration or cooling by air conditioner machine, all these are done where the room is made colder, or the body of the refrigerator inside temperature of the refrigerator is made colder by this technology. Here the work is being performed by the aid of electrical power. Okay, so the steps are involved here. The first step, A to B isothermal reversible expansion, B to C adiabatic reversible compression, then C to D isothermal reversible compression, and then D to A adiabatic reversible expansion. In this process of refrigeration, a machine is providing W amount of work on a system at temperature T2 to extract Q prime amount of heat to release Q amount. That means Q is Q prime plus W, this amount of heat, to the surrounding at temperature T1, so that T1 is greater than T2. Here, with the help of external agency, heat is flowing from a lower temperature body to a higher temperature body. Therefore, the work required must be the difference between Q and Q prime, and that value is here W. Okay, W is Q minus Q prime. Here another parameter is psi, which is the coefficient of performance, which is actually the ratio of heat absorbed and work required. Okay, in our Carnot cycle the parameter was eta, that means it was the efficiency, that was W by Q, and here it is Q prime by W. So from the Carnot cycle calculation we have already calculated, or we have here also show that this value is Q minus Q prime. So instead of W we can write Q minus Q prime here. But from the Carnot cycle calculation we have already obtained that Q prime by Q is actually T2 by T1. So instead of Q prime by Q we can write T2 by T1. So similarly the expression of psi, that means the coefficient of performance, can also be written as Q prime by Q minus Q prime. That can also be written as T2 over T1 minus T2. So this is the expression of coefficient of performance. So this is the technique of refrigeration. Here this technique is used. Okay, so that's all for refrigeration. Thank you. Have a nice day.